This is FE Peer Review, the Flat Earth Peer Review channel. The date is August 4th, 2020. The video in review is titled Flat Earth, You Have No Clue. The video is by Anti-Globe, and the video link is as shown in the title. Anti-Globe just came out with a video that asks an interesting question that I think deserves a thoughtful response. And that's what this video is going to be about. I'm going to start by playing a couple of seconds of his video where he asks his question.
How can you convince the world that the Earth has any flatness when the consensus is that there is no flatness on the surface of the Earth whatsoever?
So, how can you convince the world that the Earth has any flatness when the consensus is that there is no flatness on the surface of the Earth whatsoever? Well, a couple of thoughts on that. First thought was, well, observations of the world. Let's assume nothing about the shape of the Earth, and let's just open our eyes and look around. What if we observe something about the world, something physical and measurable about the world, and in the process of measuring it, we find that the only way for those measurements to work is if they're in the context of a flat plane. If that were the case, if the only mathematical solution that worked with the measurements we took of the world could be had on a flat plane, that would be pretty convincing evidence of a flat Earth. And conversely, if we took those measurements, if the measurements we took of the world, actual measurements, only worked on a curved surface, that there was no other mathematical solution than a curved surface, that would be pretty good evidence of a curved surface. So, to answer your question directly, how can you convince the world that the Earth has any flatness? You start by not assuming it's flat or curved. In your question, you're assuming it's flat. I'm saying start by no assumption. Don't pre-assume anything about the shape. Find some observations you can make that you can measure. And then based on those observations of the actual physical world and those measurements, you derive a shape that can be the only shape that works with those measurements. So now, what might be something you could measure? Well, I'm taking a look at the picture you chose for your video, and that got me thinking right away. Well, there you go. Beautiful. A boat traveling across the ocean, vast, undifferentiated space, just heading off to the horizon. No bumps, no valleys that you're going to have to go down into, no mountains you're going to have to go up and over and across, no rivers to cross, just a straight line. You get out there on a boat and you point yourself. Let's suppose that you're somewhere out in the middle of the northern Pacific Ocean, somewhere in the northern hemisphere on your boat. You point your boat due north, heading towards Polaris, and you travel in the straightest possible line you can towards Polaris on your boat. Let's look a little bit at boat navigation on boats. Why do they call it a knot? A boat travels at a certain number of knots. So where did that all come from? Well, this little page from the National Oceanic and Atmospheric Administration gives a tidbit of historical background down at the bottom of the screen here. A knot is 1 nautical mile per hour. So a knot is a mile per hour. It's a speed. The term knot dates from the 17th century when sailors measured the speed of their ship by using a device called a common log. This device was a coil of rope with uniformly spaced knots attached to a piece of wood shaped like a slice of pie. The piece of wood was lowered from the back of the ship and allowed to float behind it. The line was allowed to play out freely from the coil as a piece of wood fell behind the ship for a specific amount of time. When the specified time had passed, the line was pulled in and the number of knots on the rope between the ship and the wood were counted. The speed of the ship was said to be the number of knots counted. So the knot comes from this old technique for measuring the distance you had traveled, and also, because you've done that within a fixed time frame, the speed you're traveling at. And the length of a knot became standardized as 1 nautical mile. And a nautical mile, that's the next paragraph up, a nautical mile is based on the circumference of the Earth. We don't need to worry about that now. All we're interested in is how long is a nautical mile. Slightly more than a land mile, nautical miles are used for charting and navigation. Let's look at a little video I found. Here it is. This guy is on a boat, and he's showing us how it was done in the old days. I mean, this was in the 1700s that they were doing this, the 1600s, long before digital anything. They didn't even have electricity at this point, and they had to figure out how they were going to cross the Atlantic Ocean and get from the United Kingdom over to their colonies in the Northern Hemisphere, Virginia colony and all of that. They had to get across. They had to know how fast they were traveling, how many days voyage it was going to be, and they had to know they were pointed in the right direction. So this is how they did it without the benefit of any of the modern technology that we have today. This guy will explain it.
Into it. Well, it all comes in because the way you measured your knots and the way you traveled in a ship was with this. It's a ship's log. And you can see it's actually a piece of wood, which is a section of a circle, weighted down the bottom with lead. It was either a strip like that or lead plugs. It's got 3 ropes going into it, one of them being on a removable peg. The idea was this: you chuck this overboard, and that, because of the lead weighting, sat upright in the water. It didn't sink, but it sat upright. And that stopped it being dragged through the water. So when you chucked it overboard, it stayed still, and the ship sailed away from it. And you could pay out all this line, and at intervals along the line, in fact, every 14.4 meters, you would mark it with a knot. And the first one had 1 knot, the second one had 2 knots, the third one had 3. You get the idea. And the unit of time was peculiarly 28 seconds, which was measured with an hourglass. So you turn the hourglass over, threw the log out, and when the sand ran out of the hourglass, clamp on the rope and say, oh yes, that's so many knots. Well, let's see how it goes. Let's get the rope ready. I think we're ready to heave. Could you start the hourglass now? Okay, that's the end of 28 seconds. Well, let's see where we are. We're not on a knot, but just down here, not very far away, is this. What does it say? As you can see, it's got 4 knots on it. So we're going at almost 4 knots. Not very fast, but a nice leisurely pace.
So that's how they used to do it. No fancy electronics, and no way for the evil bad guys to trick your cell phone into making the Earth look round when it's actually flat. It's just a rope and a weight on the end of it. So now we've got a way to measure the distance we're traveling on our boat out in the middle of the ocean. It requires no electronics at all. No gadgets that can be messed with by the bad guys. And so now the next ingredient is to find a way to measure the angle to Polaris, the North Star. And with that, a very simple tool is an inclinometer. Again, something you can do totally analog. You don't need any digital equipment for this. So here's a little clip of using an inclinometer to find Polaris.
To do this in the Northern Hemisphere, start by locating Polaris, the North Star. Ursa Major, the Big Dipper, helps locate this important star. Extend a line from these 2 stars. They point at Polaris. Sight Polaris with your inclinometer. The angle indicated on the scale is your latitude. My latitude here is 46 degrees north.
So he has that very simple little device, just basically a piece of cardboard with a protractor printed on it and a string coming down from the center point of the protractor and a little weight to get the string to hang vertically. And he's pointing that, sighting down the top of the edge of the cardboard, pointing it at Polaris, and he gets an angle. So what you can do now is you've got an angle and a distance. So here's the next step. What you're going to do is, let me bring up my little diagrams. Let's go back to diagram 1. What you're going to do is you're going to get out on your boat and you're going to take your inclinometer and you're going to sight up to Polaris and you're going to get an angle on your inclinometer. Make a note of that angle. And then you're going to continue on your cheerful boat voyage over the sea, and you're going to travel 60 nautical miles. That's about 69 miles. So 60 nautical miles, and do that again. Get out your inclinometer, take another measurement. You're going to up at Polaris, and let's do that 2 more times. Here's a third one. You're going to get an angle that I've called C. Do that again. You're going to get an angle I've called D. You've got 4 measurements that you've taken now. You've covered this distance and you've measured from each of the 4 spots. And you can do as many of those as you want, but I would say you probably want to do at least 4. And the distances doesn't have to be 60 nautical miles, but that's a convenient number if you're able to do it, because that will match up with, well, I'm not going to say anything about what I think the results are going to be here. I'm going to just give you a technique, a method. And I'm not going to tell you what I think the results are going to be. I'm going to tell you that if you're interested, you do this and you find the results for yourself and you draw your own conclusion from those results. But I will say, a couple of different things that could happen. So let's see. We've taken 4 measurements now. We could trace all 4 of them and look at what happens. And one possible result is that you might find yourself looking at 4 different locations in the sky, but it's Polaris, it's the same star. So how can it be that you're seeing the same star in 4 different places? That doesn't really make sense. Logically, that doesn't match up. You can't see the same object in 4 different places. And I'll reinforce that by saying you can't see it in 4 different places at the same time. So, of course, you're not in 4 different places at the same time, but you and 3 buddies could be. You could each be out there in the ocean on a boat 60 nautical miles apart, and at the same moment, you could all sight Polaris and get your measurements. And the result might be that you see Polaris in 4 different places. If that's the case, then you know that there's more to this than you might have thought at first. Or on the other hand, you might find that your 4 measurements all point to the same spot in the sky. Now that would be reassuring. That would give you the feeling that you're looking at Polaris in the sky in one spot as you're moving along the ocean surface. Now you will note that I have made an assumption here. When I drew this diagram, I assumed that this surface was a straight line, flat, that we are moving along a flat plane, a flat Earth. That was just for the purpose of this diagram to show one possible outcome of your observations. I also used the same flat plane on this diagram. So let's look at another possibility. Here's another possibility. It could be that there is only one Polaris in the sky and you measured 4 angles, but the only way that you can get the geometry to work is to bend the surface that you're standing on. That's also a possibility. I'm not going to say which of these possibilities I think is correct. Could be that there are 4 Polarises and that you see a different one each time. That seems rather illogical. There's not really anything quite like that in our normal human experience. It could be that you see one Polaris from 4 different places on the Earth, the angles all match up for a flat plane. Or it could be that the only way your angles can match with a single Polaris is for the surface you're moving on to be curved. Those are, at the moment, the only 3 possibilities I can think of. Those are the only 3 possible outcomes. But you need to do this experiment yourself if you want to know which of those outcomes it actually is. With nothing more than a piece of cardboard with a angle gradient on it, a very simple piece of non-mechanical, non-electronic kit here. With a basic string to measure your distance, you can find out all you need to determine the shape of the Earth yourself. So back to your question. You started out by asking the question, how can you convince the world that the Earth has any flatness when the consensus is that there is no flatness on the surface of the Earth whatsoever? Doesn't matter what the consensus is. If you can do physical observations that you can measure, and if those physical observations can only occur on a flat Earth, then you've proven the Earth is flat. On the other hand, if you do those physical observations and they prove that there's no way for those observations to match a flat Earth, you also have to accept that possible outcome. You can't go into it assuming either thing. You do the observations and you get your evidence and you go where the evidence takes you. You don't try to force the evidence to fit the outcome you want to find. So that's my answer to your question. Do some physical observations, take some measurements, look at the results. It's up to you. You can do it. Give it a try.